Hello and welcome to today's lecture. Today we're going to introduce the notion of hyperbolic area and we are going to prove the very famous formula of Gauss-Bonnet, which for any given hyperbolic triangle relates its hyperbolic area to to the sum of its internal angles and confirms a result that we already proved, namely that if two hyperbolic triangles are similar, then they must be congruent. So let's start with the notion of hyperbolic area. Uh, we work in the upper half plane model, and given any subset of the upper half plane, we define its hyperbolic area to be this integral. Uh, as you can see, this integral is a modification of the integral that measures the usual area in the Euclidean plane, and this modification is given by making the points close to R bar very dense or very heavy, and so the regions or the regions close to R bar have actually a very large hyperbolic area, uh, because very close to R bar, this somehow some sort of weight takes very large values. That is, the points close to R bar are very dense, and this is in sync with the intuition we obtained before when we defined Riemannian the hyperbolic Riemannian metric for the upper half plane, that uh, uh, tangent vectors very close to to R bar are actually very long, and hence the distance between points that lie close to R bar um, is very large, right? So that close to R bar distances are very large. Well, now here you can see that also close to R bar areas are very large. Hyperbolic areas are very large. Um, and of course, if this integral actually exists, right? If this Riemann integral actually exists. Now, there is one step that I'm skipping. There is something that I'm not saying, which is how does one motivate the use of this integral for this definition, right? Why do I use this integral and not other integral, right? So why do I integrate this and not something else? Um, and for instance, recall that um, when I defined the length of a curve in Riemannian manifold, well, I defined it as a certain integral, um, this integral of something like AB of the norm of gamma prime of t, where this norm is taken gamma t. So this is how I defined it. And then I gave some justification, some motivation as to why this integral and why this integrand. Um, um, that's something I'm not doing here. it is possible to do it, and I leave it to you as a challenge to try to justify why this. I also leave it to you to give it a thought about how about replacing the Riemann integral with the Lebesgue integral. But this Lebesgue integration I'm not going to discuss at all in this course. And of course, we would like hyperbolic area to be invariant on the Riemannian isometries of the upper half plane. And so this theorem states that a hyperbolic area is invariant under the Riemannian isometries that preserve orientation. The general case of arbitrary Riemannian isometries I leave as a handy exercise. So here the exercise asks you to show that for every subset of the upper half plane and every Riemannian isometry, if the hyperbolic area of the set exists, then so does the hyperbolic area of the image of x under nu, and both are the same. Right? So both values, both areas are the same. This I leave as an exercise, as a handy exercise, and I'm going to prove only the theorem only for half the isometries, right? Namely for those that preserve the orientation. That is, for those that are of the form Mobius transformation of a matrix in SL2R. And I leave you the rest. Now, such a transformation, of course, is a function from u to u, right? And u is, of course, containing the complex numbers. So such a function nu certainly has a real part and an imaginary part. So, of course, it is possible to write nu as u plus iv, where u is a function from u to r, and v is a function from u also to r, giving the positive and real parts. And since nu is holomorphic on the whole u, what I can say is that its real and imaginary parts are then of class C infinity as functions from u to r. Okay, and then so I what I see is that I can write my nu here as a Mobius transformation, and also I can write it in terms of its real and imaginary parts. Okay, since you see, since I want to show that these two areas are the same, what I really want to show is that certain two integrals are the same, where to this set I apply some transformation, right? Which I think of as some change of coordinates, as when we were taking calculus, when we took, let's say, spherical coordinates, right? And then we computed integral the volume in terms of spherical coordinates, for instance. So something similar. And so this means that I have to compute the Jacobian of the change of coordinates. Now here the change of coordinates is given by u and v. So I have to compute this Jacobian, which is the determinant of the partial derivatives of u and v. Well, um, since nu is holomorphic from U to U, um, the Cauchy-Riemann equations are satisfied. So this matrix here, of which I take determinant, satisfies the Cauchy-Riemann equations, which means that um, these that these two are equal, and these two are one is minus the other, right? And hence this determinant becomes this square minus the product of this, so plus this square. Um, and I noticed that that is nothing other than the square of the norm of nu prime of z, where this nu prime of z is just the derivative of nu as a function as a complex function of a complex variable, right? Because we know that that actually the the relation between this matrix and nu prime of z is that this matrix represents multiplication by nu prime of z as a map between tangent planes. Okay, so I'm here, uh, and now if you remember when we proved that the elements of PSL2R uh, are Riemannian isometries, we computed this norm, and we arrived at this is equal to this. Okay, so that on the one hand, I have computed the Jacobian, and it's given in these terms. You see where in terms of the matrix and the point z at which I'm evaluating. So namely z is let's say x plus iy. Okay, and now so the hyperbolic area of this one, which is simply the integral of, you see here I put du dv and then imaginary square and then integrate over this one, yeah, and then I take the change of coordinates. So I can instead of integrating over nu x, I can integrate over x as long as I take the change of variables. So nu becomes, sorry, so v becomes um, v of xy, right? So it becomes the value of the function, and then here I take the Jacobian, I substitute the Jacobian, um, yeah, and then when we proved that the elements of PSL2R preserve U bijectively, we computed the imaginary part of nu, and we saw that it was the imaginary part of the imaginary part of nu of z, and then we saw that the imaginary part of nu of z was the original imaginary part divided by what you see here in the numerator. And now here you are seeing here in the denominator and here in the numerator because this v is in the denominator, right? And then square, well, square and fourth. And then I realize that there's this cancellation, and I realize that after the cancellation, what I obtain is precisely the integral that defines the area of x. And I am done. So everything relies on the formula for the formula for computing an integral under change of variables. First, uh, computation of the Jacobian, Cauchy-Riemann equations, and uh, and these computations that we had made already. When we started speaking about the upper half plane some time ago. Okay, so hyperbolic area is invariant on the Riemannian isometries that preserve the orientation, and you deal with the general case. Now let me introduce hyperbolic convexity, which is an ingredient in Gauss-Bonnet formula, but also an ingredient in when we speak about the Dirichlet polygon of a Fuchsian group in some forthcoming lecture. And so, well, uh, the first thing I want you to notice is that, so we know that any 2 points in U determine a shortest curve. Right? If I pick any 2 points, there is exactly one shortest curve joining them. But not only that, actually, if I take any 2 points in R bar, they determine one shortest curve that joins them, right? Namely, the unique segment of circle, which is orthogonal to R bar and passes through both of them. So, if the 2 points lie in R, well, I just have to take the middle point, the Euclidean middle point, and then draw the corresponding circle, right? And if 1 point is in R and the other point is infinity, then I just have to draw the vertical line, the vertical Euclidean line, right? So what I'm saying is that every pair of points in U bar determines a shortest curve, and it is conceptually better to define hyperbolic convexity for subsets of R of U bar, right? So allowing to start with sets of points contained in U bar and not only in U. So if a subset of U bar is hyperbolically convex, if for every 2 points in the set, this shortest curve segment, that here I can just take I just take the let's say the open segment, is entirely contained in C. So for every 2 points, the shortest curve joint that they determined, the segment that they determined connecting them, is entirely contained in C. And well, there's two things to note here in this definition. One is that it is the of course just the hyperbolic version of the definition of the Euclidean definition. That's one thing to note. But another thing to note is that while in Rn um, we can this segment, this open segment, can be the points in this open segment can be written as certain linear combinations of the form lambda one of the points plus 1 minus lambda the other point, while this can be done in Rn. uh, we cannot do that in the hyperbolic plane. So on the one hand, I'm really just adapting the notion of convexity I already knew in the for in the Euclidean case. But on the other hand, um, it's going to be a bit harder to deal with this notion because uh, uh, I don't have the same nice description of the points in these segments that I have in the Euclidean case. So I should expect some properties to be harder to prove or harder to deal with in hyperbolic convexity. Again, because in the hyperbolic plane, uh, I cannot really express the points in this segment as as this type of linear combination, lambda something plus 1 minus lambda the other thing. Okay, so that's a piece of warning. But um, but here this exercise shows that every subset of U bar has a convex hole. A convex hole. So first, if F is a non-empty family of H-convex subsets of U bar, then the intersection of all the members of the family is again an H-convex subset of U bar. That's very easy. And uh, 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 something to think about is why do I require the family? Why do I assert this over non-empty families? Right? What happens if I take the empty family? Okay. So, but this is a formality. This thing to think about this requirement of non-emptiness is just a formality. Um, okay, and then because of one, uh, proving the following becomes very easy. That for every subset of U bar, there exists a hyperbolically convex set that contains it, and is contained in any other hyperbolically convex set containing my set. Right. So somehow you see I have my somehow my set S, um, and what two states is that for then there exists C, which contains this one and is convex, right? So I don't know if I were thinking Euclideanly, maybe, yeah, and it's also contained in any other convex set containing it. So it's like a minimum hyperbolically convex set containing S, right? So it like it grabs around it, um, or yeah, it's like an envelope or a hole, a convex hole. So let me give you some examples. So let's say, of course, the convex hole of 2 points is just the shortest curved segment joining them. Of 3 points, the hyperbolic convex hole is what you are seeing here. It would be all of this region inside. Of 4 points, for instance, here, let me start over. Of 4 points, So of these 4 points here, I have this would be the convex hull. But if I move this here, well, you can see that the convex hull of the 4 points is this region inside. So somehow, to obtain the convex hull of the 4 points, it suffices to take the convex hull of these three. Right? But if I move it like for this other this other set of 4 points, the convex hull is all of this. So I cannot get rid of one of the points without making the convex hull strictly decrease. More examples of convex hulls. So there you have for 5 points, and then same thing. So like here to here this point lies in the convex hull of the remaining ones, and then here the 2 points here lie in the convex hull of the remaining ones, also here. But then you see here you can play around, right? So, but my point is, what I want to illustrate is what the convex hull of a set of points is, and second, that if you give me a set of points S, it may be that some of them lie in the convex hull of the remaining ones, right? In some cases, and in some other cases, it may be that none of them lies in the convex hull of the remaining ones, which makes somehow all of them necessary to span the convex set. And this brings me to the next definition. A subset is called of U bar is called a hyperbolic n-gon, or a hyperbolic polygon with n vertices, if there are n distinct points in U bar with the following two properties. First, this is their convex hull, right? But the n points, they are all strictly necessary to actually obtain D as convex hull. In other words, every time I get rid of at least one of them, the convex hull decreases strictly. Okay, so now let me finally just illustrate what I say about this U bar, right? Why I am allowing U bar everywhere here. I mean, as I already mentioned, that every 2 points in U bar determine a shortest curve, and that's and not, I mean, every pair of points in U bar determines a shortest curve, and not only every pair of points in U. So here, for instance, you are seeing the convex hull of 3 points in R bar. So all of this, what you are seeing, it's what you are seeing here is the convex hull of these 3 points, and all of them, all 3 points, lie in R bar. And what we can see then is that what we are allowing is we are allowing triangles whose vertices, or at least some of their vertices, lie in R bar and are not finite points. right? So that's the point, that we are ultimately allowing hyperbolic polygons that may have some points at infinity as vertices. For instance, this triangle that you are seeing here, this hyperbolic triangle that you are seeing here, which is this part inside, which is h-convex, and it's the convex hull of these 3 points, has two finite vertices and one point at infinity as another vertex. Right? So that's the point here, to allow points at infinity to be vertices of polygons. And now the Gauss-Bonnet formula, which states that if you give me a hyperbolic triangle that is, you see here, when for n equal to 3, so that there are 3 distinct points, such that you see in this delta is the convex hull of the 3 points, but if I get rid of at least one of the points, I cannot obtain the whole d, the whole delta. In other words, those 3 points are not hyperbolically collinear. Well, if you give me one such hyperbolic triangle with these internal angles, alpha, beta, gamma, and I allow some of them, or even all of them, to be equal to 0, which is what happens precisely when the corresponding vertex that the angle subtends is a point at infinity. So the angles in a hyperbolic triangle, any angle equal to 0 actually subtends a vertex of the triangle, which is a point at infinity. Okay, but regardless of whether some of them are 0 or not, but the area of the triangle is always pi minus the sum of the angles. And then, before going into the proof, let me say some things. So first of all, notice that then this means that in a triangle, in a hyperbolic triangle, the angles never add up to pi, because then I would have a triangle with area equal to 0. So try to imagine a triangle with a hyperbolic area equal to 0. So which is kind of in a way is kind of in the complete opposite extreme to what happens in the Euclidean plane. In the Euclidean plane, for every triangle, the sum of the internal angles is pi. Here it is never pi. It's not that it sometimes fails to be pi. It's that it is never pi. That's the first thing. And then the second thing is to notice is that the size of the triangle is determined by the angles, which, if you think about it, is completely in sync with what we proved the last time when we used the second law of cosines in the hyperbolic plane to show that if two triangles have the same internal angles, then the lengths of the opposite of the sides also coincide, right? And then there's actually an isometry taking one triangle to the other. So this theorem is in sync with this idea that triangles in the hyperbolic plane are actually very rigid objects, right? It's impossible to rescale them non-trivially, right? Because rescaling them non-trivially somehow, you see, if you change the sizes of the sides, and you cannot do it without altering the angles in the hyperbolic plane. Okay, now we are going to prove Gauss-Bonnet's theorem in two cases. In the first case, we are going to suppose that one of the vertices of the triangle is a point at infinity, or equivalently, the corresponding angle that subtends it is equal to 0. So somehow the generic picture would be that one vertex is a point at infinity, and the other two may be or may not be points at infinity, yeah. But somehow, okay. But then you see, up to applying a Mobius transformation, I can send this one to infinity, right? I mean, to infinity in C bar. Without changing the value of the hyperbolic area of the triangle, because of the first theorem we proved today. So, without loss of generality, I can assume that, you see, here is the upper half plane, and so first of all I can assume that the third vertex is the point at infinity. So the angle gamma is 0, but it's kind of infinitely far away. Yeah. That's the first thing I can do. The second thing is, of course, once I have that here the angle gamma here is 0, but that the corresponding vertex is infinity. Once I have that, then I can, of course, translate horizontally. Yeah, and multiply by positive real numbers, so that my triangle becomes, you see, that the side opposite to gamma is a segment of the Euclidean unit circle centered at the origin, right? So first we can translate horizontally to put the center nicely, and once the center is nicely put, then we can rescale with a positive real number, so that this is really, it's a radius, Euclidean radius 1. And all of this we can do without altering the value of the hyperbolic area. Now, okay, what we once we have done that, we notice, like we did last time, that these angles, alpha and beta, which really are, you see, the angles that this side forms with the tangent to this side, tangent at this point, and similarly for beta, although for beta it's not drawn. That angle alpha is equal to this angle alpha, and this angle beta is equal to this angle beta, like we proved it last time, right? Which is a simple argument that alpha plus 90 plus this is 180, and this one plus 90 plus this one is 180. So this one has to be equal to this one. And similarly for beta. We notice that, and we project, and then this is the coordinate, let's say the x coordinate to be A, and the x coordinate, let's call it B. And now we want to compute the hyperbolic area. By definition, it's this, right? But then you see we want to integrate over this region, which is in the infinite region, right? So, and then what we do is what we have to do is just parameterize this and then integrate this that way, right? So the parameterization of this is here, and then for each x we just go to infinity, and then this is what we integrate, right? So that's basic calculus. Now for fixed x, this integral is a limit. It's a limit of the integral where on all up to t, right? But okay, up to t of what? Well, this one is easy to integrate to find an antiderivative, right? And so antiderivative from lower to t, and then t goes to infinity. Okay, again basic calculus. I plug in, and when t goes to infinity, this goes to 0, and what I just want you to see is that somehow for finite t, somehow I'm subtracting something small from this number, from this positive number. And in any case, when t goes to infinity, I end up not subtracting anything. So it's this integral, change of variables, right? I mean, here it's what change of variables I'm using, right? And of course I have to I replace dx with the derivative, right? And then d delta. So with the derivative and then d delta. Okay, but here of course this cancels, and then I have the integral of minus 1 from pi minus alpha to beta. So it's minus theta from pi minus alpha to beta. Okay, but then, okay, obvious, right? I mean, minus beta, and then minus minus beta minus pi minus alpha. Okay, so pi minus alpha minus beta minus gamma, because gamma was 0. Okay, and then the Gauss-Bonnet formula has been proved in the case that one of the vertices lies at infinity, or equivalently one of the internal angles is 0. And now what remains? Well, we still have to prove Gauss-Bonnet's theorem, for in the case where all three vertices are finite. Okay, so let's say that this is my delta. All three vertices are finite. And then what do I do? Let's say I pick one of the vertices, let's say this one, and what I do is I take one side. You see, from the sides incident to the vertex, I start going, and then I just keep going towards until I hit a point at infinity. Yeah, and then from this point at infinity, I just close a triangle to the other vertex, and then close the triangle. So that's what I do, so that somehow I force a vertex at infinity. And the point is that for this delta tilde, which is the bigger one, I already know that Gauss-Bonnet formula holds. Namely, I already know that the hyperbolic area of this tilde is pi minus this plus this, right? Because my delta tilde is this one, so I have to subtract this plus this. This is 0. Right? Okay. Now this is alpha. It's been subtracted here, and this one is gamma plus something that I'm going to call delta. Okay, so this we know from the first case that we already proved. Now, on the other hand, this one can be written as this overlapping union, which overlaps only on this side. Overlapping union of this one and this one. So this one, well, its hyperbolic area is this one precisely, which is the one we want to compute. And the other one, well, again, it has this vertex at infinity. So we can apply the known case of Gauss-Bonnet to see that this area is pi minus this, which is the theta I said before, plus this. But you see here, this plus this is pi. Right? So this is pi minus beta. So the area of this guy is pi minus theta minus pi minus beta. Okay, so this means that when I consider, you see, just this equality, this pi, well, this pi cancels with this pi, and then this theta, it's minus theta here, and then this theta appears also with this minus, so it cancels, and then this minus beta, this minus becomes plus beta, which then I can move to the other side as minus beta. And what I obtain is that this one is this with the beta moved to the other side with a minus, and this is exactly what I wanted. And this finishes the proof of this beautiful formula of Gauss-Bonnet, which, as I said, it gives us a very good feeling or intuition of the rigidity of triangles and polygons in the hyperbolic plane. And finally, some homework. So here is the hand-in exercise. Yeah, so that to show that hyperbolic area is invariant under all possible Riemannian isometries of the upper half plane. Here you have this this other exercise, which is generalized Gauss-Bonnet formula to arbitrary n-gons.